In this last video for today, I want to introduce one new concept, which is the trace. Nothing complicated, actually very easy. And how to use it, use that in combination with the determinant to have some relationships for the eigenvalues of a matrix A. If our matrix A is 3 by 3, for example, then the trace of a matrix is just the sum of diagonal terms. So for an n by n matrix, the trace is given by a11 plus a22 plus a33 plus a and n. And if you don't like to think about this expression in terms of the 1, 1, 2, 2, 3, 3 notation or in terms of letters, just think about the fact that this is the sum of terms along the diagonal. Now, the trace has the very interesting property that it is not only the sum of the diagonal terms, but it is also the sum of the eigenvalues of a matrix. Furthermore, we know about the determinant. So the determinant of a matrix A is not the product of the diagonal terms. It is the product of the pivots, which happen to coincide in triangular matrices with the diagonal terms. But no matter whether we have a diagonal or matrix or not, or a triangular matrix or not, the product of the eigenvalues is given by the determinant of the matrix. So you see here we have two equations, fairly easy, for maybe n unknowns. So you see these two equations cannot uniquely determine our eigenvalues, but they can be a good way for us to check if maybe we've made a computational error in trying to find the eigenvalues of a matrix. So if you have that the sum of your eigenvalues is not equal to the trace, or if you have that the product of the eigenvalues is not equal to the determinant of the matrix, then you know you've made a mistake. Furthermore, you see two equations can only solve two unknowns, so you could potentially eliminate one of the eigenvalues. If you found the first n minus 1, then you know that the nth eigenvalue will be the trace minus that sum. So that's another way. Like if you have a 3 by 3 matrix and you've found two eigenvalues, let's say the matrix was maybe a Markov matrix, so you know that 1 is an eigenvalue. And let's say that the matrix is singular, for example, so you would know that 0 is an eigenvalue. Then this would tell you what the third eigenvalue must be. So the trace can give you that third eigenvalue. From here too, you can eliminate one unknown, but the point is that you can use the trace and the determinant of the matrix immediately in the case of a 2 by 2 matrix. So for example, if we go back to our Markov matrix that we had in the previous video, it was 0.8, 0.2, and then 0.3, 0.7. So you see that each column of the matrix A adds up to 1. That tells you that 1 is a that the matrix, that 1 is an eigenvalue because this matrix is a Markov matrix. So we know that A is a Markov matrix. Again, how do we define a Markov matrix? Each of these terms has to be a number between 0 and 1, possibly 1, possibly 0, but between 0 and 1. And the sum along each column needs to be 1. That is the definition of a Markov matrix. So since A is a Markov matrix, we know that lambda 1 is 1. So we know one eigenvalue. The matrix is 2 by 2, therefore it has two eigenvalues. Now using the trace of A is 0.8 plus 0.7, these are the diagonal terms, which is equal to 1.5. On the other hand, the trace of A is lambda 1 plus lambda 2. So what do we have? We have that lambda 1 plus lambda 2 is equal to 1.5. And lambda 1, furthermore, is equal to 1. So directly from here, we can see that lambda 2 equals 0.5. Now, what about the second example that we saw? So this is example 1, for example. What about example 2? So we had the matrix 1, 2, 2, 4. Now this matrix A is singular. What that tells us is that the determinant is 0, but it also tells us, and if the determinant is 0, that means that one eigenvalue must be 0. So we have lambda 1 is 0. On the other hand, the trace of A is 1 plus 4, which is 5. And we know that the trace of A is lambda 1 plus lambda 2. So it must be the case, since lambda 1 happens to be 0, that lambda 2 is 5. So we can do, for a 2 by 2 matrix, we really don't want to get the eigenvalues wrong because we have alternative ways to solve them. Now, of course, I could give you a completely a different matrix that that's not Markov and it's not singular, where you can use the two formulas, the determinant and the trace. So for example, let's look at the matrix 1, 2, 3, 4, let's say. So what we know is that lambda 1 plus lambda 2 is equal to the trace of A, which is 5. And lambda 1 times lambda 2 is the determinant of A, which is 4 minus 6, which is negative 2. So we know that the sum of the two eigenvalues is 5, and their product is negative 2. So how do we find them? Well, let me rewrite the system. Lambda 1 plus lambda 2 is 5. Lambda 1 times lambda 2 is negative 2. Of course, you can't use Gaussian elimination here because the second equation is not linear. The two unknowns are multiplying each other. But you have seen these types of problems in high school, hopefully. You can just use one of these functions, one of these equations, to express one variable in terms of the other. So for example, I could say that lambda 2 is 5 minus lambda 1, and use that inside the second equation, where we will get lambda 1 times 5 minus lambda 1 needs to be equal to negative 2. Now, this is a quadratic equation that we can solve. To do that, we bring everything to the same side. So we have lambda 1 times 5 minus lambda 1 plus 2 equals 0. So we have 5 lambda 1 minus lambda 1 squared plus 2 is 0. And I do want my lambda 1 squared to have a plus sign, so I can multiply everything by negative 1 and essentially change the sign. So this one will be minus, this one will be plus, and this one will be minus. And I will want lambda 1 squared to be first. So I have lambda 1 squared minus 5 lambda 1 minus 2 is 0. And now I can find the solutions to this equation. You can tell that this example was not cooked up. We're not going to get whole numbers. So to solve this problem, I actually have to use the quadratic formula, which, anyway, you can try to do. It's not important. I just wanted to show you how you can use the two equations only in the 2 by 2 case. For us, I will mostly want you to pay attention to these facts. If you have a Markov matrix, you already know one of the eigenvalues. In fact, in general, if you have a matrix, any matrix, whose terms in each column add up to the same number, whether these numbers are between 0 and 1 or not is irrelevant. If they add up to the same number, then that number will be an eigenvalue. And then look for singularity. If your matrix is singular, you also know one eigenvalue. So if I gave you this Markov matrix here, for example, 0.1, or maybe not even a Markov matrix. Let's not do a Markov matrix because that's kind of where I'm going with it. Let's say we have 1, 3, 7, and then I have 7, 1, 3, and then I have 3, 7, 1. You see, you know that the sums along each column will be the same. In fact, the way I've written these matrices, we also have the same sums along the rows, but that's not important. You know that when you do A minus lambda I, and let's immediately look at that determinant, we will have 1 minus lambda, 7, 3, 3, 1 minus lambda, 7, 7, 3, 1. 1 minus lambda. I'm not sure why I did only 1 minus lambda along the diagonal, but I was inventing it in the moment. Now, if here I add everything to the first row, so if I do row 1 plus row 2 plus row 3 into row 1, which is an allowed operation, this operation doesn't change my determinant, I will get 11 minus lambda, 11 minus lambda, 11 minus lambda in the first row. And then I will get 3, 7, 1 minus lambda, 3, 7, 1 minus lambda. So now I can factor this 11 minus lambda. And then I have the matrix 1, 1, 1, 3, 1 minus lambda, 7, 7, 3, 1 minus lambda. And now I can eliminate with that 1. What is going to happen is I'm going to have 11 minus lambda, 1, 1, 1. Then I have to subtract 3. So the operation is R2 minus 3R1 into R2 for the second row. So I will get 0. Then 1 minus 3 is negative 2 minus lambda. Then 4. And then the operation in the third row will be R3 minus 7R1 into R3. So I will get 0. 3 minus 7 will be negative 4, and then I have 1 minus 7, which is negative 6 minus lambda. And now, if we do expansion along the first column, we see that this is simply 11 minus lambda times this smaller determinant, which is 2 minus lambda, 4, negative 4, negative 6 minus lambda. So I know right away how to reduce that system. And I guess the point I was trying to make, I sort of lost it a little bit there. The point is immediately I knew that lambda 1 had to be 11. Now what else do I know? Well, I know that lambda 1 plus lambda 2 plus lambda 3 must be the trace, and the trace is 3. So if I substitute 11 for lambda 1, that gives me lambda 2 plus lambda 3 is equal to 3 minus 11, which is negative 8. And then I know that lambda 1 times lambda 2 times lambda 3 equals the determinant of A. So if I compute that, you see what happens is I've eliminated one variable. I know that lambda 1 is 11. So what I know from here is that lambda 2 times lambda 3 is the determinant of A over 11. So I have dropped my variables. Now, if I also knew, or if I had cooked this up in such a way so that I have A to be singular, if my A was singular, I would know 2 eigenvalues, and then I would be able to compute the third one using the trace and the determinant. Again, you don't always have to use the trace and the determinant, but sometimes that can be very useful. Okay, done for today.